So now we'll define the concept of divisibility, and we'll use letters to denote numbers or integers, so A, B, C, etc. will denote numbers or integers from now on. So if we say that an integer A is divisible by an integer B, that means that A must be equal to B times some other integer C. And we can notate the fact that B goes into A, or A is a multiple of B, or B divides A by this bar notation here. So B divides A, and this is a very common notation in number theory. So this means that B is a divisor of A, or A is divisible by B. These are all different ways of saying the same thing. And for any number A, we can of course see that 1 divides A and A divides A. And if B does not divide A, we write B does not divide A. So these are some basic notations that you will find commonly in discussions of divisibility. And divisibility is an important concept in number theory. And one final point on divisibility: if B divides A and C divides B, then it must be the case that C divides A. And also, if B divides A, B times C must divide A times C. In other words, if B divides A, then we can multiply both B and A by some number C, and the product BC will always divide the product AC. And if B divides A and C divides B, then C must divide A. So these are some simple results about divisibility. Okay, so we'll define prime numbers now. So number P is prime if there are two conditions that must be met. First of all, P must be greater than 1. Secondly, P has no integer divisors except P and 1. So if both these conditions are met, then P is called a prime number. Numbers which are not prime are composite numbers, because they do have integer divisors other than P and 1, so you can decompose them into their smaller factors. So we'll explore that idea more in later videos. So that's the idea of a prime number, and we'll get into defining our very first theorem now. So theorem 1. So theorem 1 says that every positive integer other than 1 is a product of primes. So the proof is fairly straightforward. We can start by looking at different cases. So if we have the number n that we're interested in factorising, or we're interested in showing that any number n is a product of primes. So if n itself is prime, then we're done. It has no integer divisors other than n and 1, by definition of being a prime number. So if n itself is prime, then of course it's a product of primes. Interesting case is if n is not prime. So if n is not prime, then it must be composite. So if it's composite, it will have divisors between 1 and n. So if we say that the smallest divisor of n is m, so m divides n, and n is the smallest number which divides n, n must be prime, because otherwise there would exist some number L such that L is between 1 and M, so it's greater than 1, smaller than M, and L would divide M. So these three conditions cannot, well, M has to be the smallest number and has to be prime by this argument, that otherwise there would exist an L between 1 and M which divides M. And if L divides M, that implies that it also divides N, because we saw this in the first video where if A divides B, then B divides C, then A divides C. So that would contradict the definition of M being the smallest factor of N. So there can't be any number smaller than M which divides N. So therefore N is either prime or it's divisible by a prime less than N. So if that number was P1, say, the first prime, then we could say that N is equal to P1 N1. Again, N1 between 1 and N. Now so we factored N into the product of a prime number and another number. Now if N1 happens to be prime, then we're done. We've factored it into a product of primes. But if we again find that N1 is a composite number, then we can repeat the argument as above, find the smallest factor of N1, which is prime, just like M in the original argument. Repeat the step again, and we'll create a longer chain of primes, P1, P2, N2, and if N2 is prime, then we're done. If it's not prime, we repeat, and we can just get a longer and longer chain until we eventually run out of prime factors, and we'll have a full prime factorization of a number N, and therefore any number greater than any positive integer except 1 can be decomposed as a product of primes and is a product of primes.